Thanks for being here, the most patient of all the students. This is the last two lectures in the summer school. And finally, we get to get a talk and think about discrete, not only discrete, but continuous choices. So the schedule calls for 2 more lectures. And this is a methods talk on the endogenous grid point methods. And then the next lecture is an application. But I would like to take an opportunity to be a little bit flexible about it. So, let me not try to go as fast as possible and kind of give you a better understanding of the methods. The motivation is very simple. Continuous choices are important, right? We kind of tend to model discrete choices separately from continuous choices in different applications. But things like how much to work and when to retire, or when to become an entrepreneur, how much to save, when to buy a house or any other durables, which car to buy and how much to drive. Life is full of important combinations of discrete things that you can do and continuous things that you have to decide. And then, of course, it's kind of useful to consider these choices separately because we have different methods. For discrete choices, we have to optimize over finite sets, and like for continuous choices, we can use first-order conditions and things like that. It turns out that in combination, things become a lot more harder, and that's probably one of the reasons why you don't see a lot of combinations. Oh yeah, and I guess I have to say that when you actually have to have a combination, then a typical approach is to discretize the continuous choice and just convert everything into the discrete choice framework. All right, so we will see in this talk that a combination of a discrete and continuous choice in the dynamic model brings you kind of the intrinsic non-concavity of the problem, and that makes it pretty hard. Suddenly, your first-order conditions are not sufficient. You will have kinks in the value function and discontinuities in the policy function, and that's a lot of fun, okay? If we kind of try to jump at this at the face value, then we will need a global optimizer at each point of the state space in order to find that, global maximum over the continuous choice in presence of local optima, which is typical, or which is what you have to face in the non-concave problem. We may have to locate and keep track of the kinks and the discontinuities in all these different objects that we work with. And also, once we have to work with these non-smooth objects, then we have to adjust our kind of typical normal numerical methods like quadrature points, for example, or quadrature integration. Because suddenly this is not going to be applied, at least formally, to the non-smooth objects. But the endogenous grid point methods is a collection of methods which make it a little bit more tractable, I would say. So on one hand, the problem is really complicated. And on the other hand, there is an approach which allows you to work with that. And that's what I want to talk to you about today. So there are 3 or even 4 parts to this talk and to this whole topic. There's the original EGM. And that's a wonderful, wonderful method for a simple problem. Okay, and we'll start there just to make sure that we are all on the same page to understand the main idea of what's really a trick here. It's a model for essentially consumption savings, but you can have all sorts of randomness in this model and such. Now, DCEGM is going to be a combination of the original EGM with the addition of a discrete choice. And this is where things become really hard. But it's very instructive to understand why they become hard and what actually breaks in the problem, in our approaches to this problem. So I say nasty and scary. But then you have to, you have an option of adding this magic power of the extreme value type 1 distribution. Or in fact, any continuous distribution with full support will use our favorite because it's just analytically much easier. And then, this also applies to models with one continuous and additional discrete choices. What the addition of the Tayshock does, it smooths the discontinuities and kinks. Okay, and here it's very important to say that it does not convexify the problem. So the problem may still remain non-convex with the issues attached to that, but at least it becomes more smooth. And I say more because it's, it's a little bit on the try and error still kind of in ground. Yes, I have a question.
You're highlighting the one continuous and then some discrete stuff, so I'm guessing it gets very, very hard once there's more than one continuous choice.
That's right, yeah.
Okay. And then we're in max or land at the end.
Well, and this is part number 4. Multidimensional extensions. And this is an active area of research. So I've been updating the slides pretty late yesterday because of the new papers, in particular by the guy sitting in the back there. Alan, hi. So there is hope to work with multiple continuous choices. Okay. And we'll talk about that too. Okay, so let's start with EGM. Endogenous grid point method. It's a fast method for solving dynamic stochastic consumption savings problems. Let me just say right out in front, right, that it applies to both finite and infinite horizons. That question comes up a lot. You should have a strictly concave and monotone differentiable utility function. That's the situation, that's the case where it really shines. If you don't have that, then you probably need some additional, solvers and numerical method, and it's less attractive. So let's stick with this case. One continuous state variable, and think of wealth, and one continuous choice variable, think consumption. And wealth and consumption is going to be the example that I'm going to use throughout. You can already kind of feel that there's a special connection between these two variables. The state variable would represent some sort of a stock, and the choice variable will represent some sort of a utilization of that stock. So we have to have this particular structure on the law of motion of the state variables. But interestingly and nicely, it will accommodate the borrowing constraints really efficiently, kind of natively. So when we go to the DCEGM, first we're going to add this additional state variables. And you could actually do it with EGM as well. But I've included this here to keep the first part really pure. So the additional maybe discrete or probably discretized variables will have to have transition probabilities which are independent of M. And then we are adding a discrete choice variable. And I say one with a star here, because of course with discrete choices you can reparameterize any number of discrete choices as a single discrete choice. So there's no restriction on how many options you have in this discrete choice. So let's think about the models with one continuous and one discrete choice. And as I said, there are two flavors. One which is kind of deterministic, and that's what we will be looking at in the first. And then there's a version with discrete choices and taste shocks, which will be much pleasant to work with. If you fall asleep during the lecture, these are the points to remember. If your model has one continuous consumption choice and one additional discrete choices, use DCEGM. It's about 100 times faster than anything else that you can come up with, and it's much more accurate. If you are lucky to work just with consumption savings model, it's about 3 orders of magnitudes faster. There's like no thinking should be done. You just go to endogenous grid point methods. Okay? Maybe you have a consumption savings model which you estimate or solve for many different situations for each person in the population or something like that. You can do it because this is so fast and precise, very precise. That's kind of like magic. The reason it's good is that it avoids all root finding operations. So we will represent the solution of this stochastic dynamic problem, stochastic dynamic programming problem. We will represent the solution as a parametric function, which essentially means that I have a free parameter that I can move as I want, and the solution will be calculated as a pair of numbers from this parameter, and the pair of numbers will basically give you the state and the action where action is optimal for that state. No equations to be solved. You just basically run through the parameter, and get your solution out of it. Well, I say if utility is separable in continuous discrete choices, then things are particularly good, and we'll talk about that. And then with extreme value taste shocks, the problem is smoothed out but not convexified, so it's still interesting from my point of view, and it's much better behaved. Okay? Right, so let's start with EGM. Simplest consumption savings model, Phelps model. The value function is going to be dependent only on one state variable, wealth. You're choosing your consumption between 0 and how much money you have, current utility and the expectation value. We will first work with deterministic return on savings, and you can see that there is no income anywhere here. Let's the utility function be CR array. I'm kind of fuzzy about this -1. When I don't see it in the papers, I'm thinking, that doesn't converge to log, and then it's not that beautiful, so please put -1. The solution is analytical, as many of you know. Here's the expression for the value function, and now we're kind of reparameterizing it to be the number of time periods before the capital period T. And what's happening here, it approaches the log, and this is the optimal consumption function. You can see that this is the linear function of your wealth. This is really convenient to have an analytical solution and start whatever you do numerically with models, with cases which actually have an answer, because then you can really well and nicely debug your code. Right? And then you take an analytical case and you try to replicate it. And we'll try to do that. Okay, just to make sure that we're all on the same page, I'm showing here the solution of this model, right? And the solution is a collection of value functions. This is state variable on the axis, our wealth, and these are the values of different points of wealth. And why are there many? Why is the solution represented by a set of value functions? Yeah, I mean, I'm also kind of tired, and probably it's just too simple, but please speak up. Well, I want you to think of this as a finite horizon problem right now, and in the finite horizon problem, everything is going to be time specific, right? And so a solution is a collection of value functions, one for each time period. Now, if I look at the optimal consumption, same story here. If you have nothing, no more future, then you just consume everything. And the optimal consumption is just a 45-degree line, which doesn't look like very much like 45-degree line, but that's what it is. And on this picture, I'm going to ask, where's the infinite horizon solution? No, that's when you get the minus infinity in your every period return. Yeah, the bottom one, right? So now imagine that instead of solving a finite horizon problem, we're doing time iterations of some sort, value function iterations. We start with some policy function, and then we solve the model until convergence. And here you can really see this convergence. I mean, everything converges to this optimal consumption function. That's where you stop, right? You will have some tolerance on your iterative procedure, and as the optimal consumption function stops changing too much, what's going on here? Then we're done. So this bottom line here is the solution of the infinite horizon problem, and this is to illustrate that we will be able to solve both types. We can reconstruct all of this solution functions and also all of the value functions. By the way, here there's also convergence, uniform convergence to this top one, but it's kind of harder to see. In the infinite horizon problem, there will be a solution, a value function that solves the problem. Okay, so that's our analytical case. Let's look at the Deaton's consumption savings model with some income, right? And so my intertemporal budget has changed over here a little bit. And again, this income may be stochastic or deterministic. We'll look at both cases. And suddenly, you know, I've added this little element and there's no analytical solution anymore, but we can apply our methods and then compare them to the case with y equals 0. And as I said, this is a really, really good practice. Whatever model you're working with, it's always a wonderful idea to have a parameter that you can put to a known value, and then you know the solution, then you check your code. Okay. Okay, so traditionally, how would we solve this model? Dynamic programming, backwards induction, or we start with some you know, capital T and then iterate to convergence. Doesn't really matter fundamentally. We first fix the grid over the state space. And if you think about this in the finite, in the discrete choice models, we kind of usually have, or we imply that the state space is discrete or discretized. Here it's a different story. Here this is wealth, or your resources in the beginning of the period. And you have to actually consciously decide that, okay, I'm going to bound this M. I'm going to solve the problem until, you know, so many $1 million or whatever. And then I want to put some grid points on M in order to be able to solve the problem on my computer. And then we do the backwards induction, right? For the final time period, we maximize the utility. We get out the optimal consumption rule. And then we iterate backwards in the usual manner by solving the Bellman equation. And now here we're solving the optimization problem with respect to continuous choice. And so again, you can discretize this. You can discretize C, and then just solve for you know, the best choice of consumption on the grid. You could also discretize the future M, and then kind of back out C. Put a grid on a different variable. That's also a possibility, which I think is a worse choice. Or you could be, you know, precise and keep this really continuous and invoke some sort of iterative solver or optimizer like Newton method, right, to find the actual optimal C. Okay, in this lecture, I'm actually showing you the code. And so the repository has both MATLAB and Python implementations of this. But everything is kind of set up in let me put it here, in MATLAB. So I'm gonna run MATLAB. Let's do this, right? Sorry. It's supposed to work very well. And you're supposed to see what I'm typing. CLC. Can you see anything? Yeah. Like that, right? Okay. So the code is here. This is the MATLAB directory in the repository. And you can see that it has many files. I'm just going to work with the Deaton model here. And this is an implementation of the model. All of the parameters are kind of fixed in this class. And then there is a bunch of methods here to work with this model. We're not going to spend much time there. I'm happy to answer questions if you have any questions. Let's just run this model. So the first thing we do, we essentially just kind of establish this object with the model. And for that, I will have to run DSE init. Hopefully it works. Yeah, OK. So now, oh, by the way, if you don't see the usual MATLAB interface, there is a very good reason for that. So Bertel and I were writing C code as dynamically linked libraries to MATLAB, and then it crashes so much that you don't really want the interface. You just work in your terminal, right? You start MATLAB without the interface, and then you edit code in a separate editor.
Simply talk too much.
Yeah, we talked.
But we can circumvent that.
Thanks. Okay, this works. It needs to be a green button, green light here, right? Yep. Okay. All right. So anyway, this is the code. I'm going to close this. And so I'm just going to run this solve VFI. And you know, each dot is actually indicating that one point in the state space is solved, and this is a not very long time horizon. It's just 25 periods, but you know, it takes some time to solve for the optimal continuous choice, optimal consumption, and we get that picture that we expected. Okay? So what's the difference with the picture that I showed before? The difference is right here. And that's why this solution is not analytical anymore. So if you have income, then you can consume everything that you have for some small value of wealth, right? And otherwise, the optimal consumption is that function over here. All right. Now back to the lecture. Is it here? It's here. Right. So just a quick reminder about the early equation. We have a Bellman equation. We have the maximization problem in here. If we write the first order conditions for this maximization problem, we get something like this. And I'm not going to be worried about the second order conditions. For now, from the envelope theorem, we have this expression where we differentiate the value function itself. We notice that we get pretty much the same thing here. And from this, we conclude that the marginal value function differentiated with respect to the states, to the wealth, is the same as the marginal utility evaluated at the optimal consumption. And that gives us the usual and familiar early equation. So what does the early equation do? It characterizes the optimal level of consumption in period t and in period t plus 1. I'm not going to simplify yet completely, so we will still have the expectation here. We need the expectation of the marginal utility evaluated at the optimal level of consumption in period t plus 1 with respect to whatever is stochastic in the model. And so in this example, it's the return. Okay, and appropriately weighted, that has to be equalized with the marginal utility of consumption today. We can use this in solving for optimal consumption. Again, fix the grid over M, fix the space on which we are solving the problem. And then in the terminal period, we can solve the same maximization problem as before. And then given this optimal policy function in the next period, which comes out of the backwards induction, right? We can solve the early equation in C by treating in each point of M, the M grid is fixed, by treating this as an equation. Is it clear? So given the policy function in t plus 1, and given the grid over mt, I can just solve the early equation to characterize my optimal choices of C in period t. And this is perfectly fine. I mean, it could have problems within the non-convex settings, right? Because this is just a first order condition, but in the simple problem, it's going to be fine. Yes?
It might be a very stupid question, but I don't understand how do you rely on the terminal period?
Yeah. How does it work? Yeah, OK. So in the infinite horizon, this is going to be my initial guess of the policy function, or initial guess of the value function. Sorry, we're here. So you start with an initial guess, and then you iterate on the Bellman equation. That's essentially what we're doing here. And you're recalculating that guess of the value function many times. Bellman equation is a contraction mapping, and so the initial guess doesn't matter. So why not make it optimize the utility function? It's actually not a very bad guess in the infinite horizon problem. Is it good? I mean, you could start with just zeros here, and that would correspond to like solving from capital T plus 1. When the decision maker is already dead, there's no value, value is 0, and then you go one step back and you get this. And the same thing here, right? It's just kind of we start with that policy function. Of course, in the simple problem, this is going to be just consuming everything you have, right? So the solution in there is just the corner solution C capital T star equals M capital T. OK. Right. OK, so now we get into the EGM territory. So imagine that Imagine that, no, that's the next step, next slide when you imagine. So what's the problem with this numerical stuff? It's relatively slow, iterative numerical optimization each point of the state space. If you happen to have to deal with a non-convex problem, then first order conditions might not be enough, and then you have to actually modify the optimization in each point of the state space in order to somehow ensure that you get a global optimum. Now, there's a loss of accuracy. So here I'm thinking about the problem with credit constraints, and we'll look at that in more detail. But imagine that point somewhere at wealth. There's a point of wealth where you are kind of transitioning from the constraint solution to the interior solution. And it turns out that there's a lot of loss of accuracy potentially if that point is not found. And we'll come back to that. On the fixed grid, it's basically impossible because you would have to know it beforehand. All right. Yeah, and so if no iterative methods and each point of the state space, that would be, if we didn't have to use that, that would be a lot better, right? A lot faster. Okay, how does it work? This comes from Carroll, 2006. We are about to celebrate the 20 years anniversary of this paper. It's a very short paper, very accessible. So the idea is this. Instead of searching for the optimal decision in each point of the state space, that's what we've been doing so far, okay? We will be looking for the state space variable, for the value of the state space, level of assets, where an arbitrary chosen decision would be optimal. So it's like turning the problem on its head. So I'm going to say, OK, imagine that I'm going to consume this much. How rich would I have to be for this level of consumption to be optimal? OK? And you can see that now the level I didn't say it right. So if I consume this much, what level of wealth would I have to have in order for this consumption to be optimal? You can see that now the level of wealth becomes endogenous, in a sense, in this numerical procedure, because I start with the level of consumption. And this is the main idea of the whole method. So how does it work? Again, I'm going to be looking at the finite horizon problem, but as we already discussed, this applies in exactly same steps to the infinite horizon problem. So imagine that I start with saying that my optimal thing to do is to consume everything. You know, and this totally applies to the finite horizon problem. Now, I'm going to be talking about this A, and this is just a number, okay? I will be going through a grid of A's later on. But let's start with just one number A. And I will be thinking of this A as to represent what's left after the consumption choice. So the A we should understand as MT minus CT, okay? But imagine that I know this and I fix this. That means that my next period wealth is well defined because this is just an R times A. That's whatever I'm left with after the choice of consumption, you know, times deterministic. If it's stochastic, then there will be an expectation somewhere. But think of this as a deterministic number now. But now, once I know the MT plus 1, then I can use the next period optimal policy function, which we'll have to interpolate on some grid. But we have computed that on the previous iteration to find the CT plus 1, which is the optimal choice of consumption in the next period. And now I have the CT plus 1. I can plug it into the right-hand side of the early equation, okay? And now again, like I've mentioned, if R is stochastic, then we have to have an expectation there. In the simpler cases, we don't. But I find this level of optimal consumption tomorrow, and I put it into the marginal utility tomorrow. I calculate the expectation, and I can calculate the whole right-hand side of the early equation, right? And now imagine that the marginal utility is invertible analytically. For CR array, this is going to be true. For log, it's going to be true. For CES, it matters, or it depends. But imagine that this is invertible. And that means that this analytical expression now gives me the optimal level of consumption today. Okay, is this clear? Now, if I know the optimal level of consumption today, and I know this A, which I started with, then I can reconstruct my wealth by just adding them together, right? I mean, it was the optimal consumption and whatever was supposed to be left after the consumption. That gives me my point in wealth. That's the amount of wealth that I needed to have for this A and the corresponding level of consumption to be optimal. Okay, does it make sense? Let me go through this once again. So I take an A, and I will have to go through a bunch of these different A's, which represents the amount of money after the consumption choice. Given this A, in this model, I will be able to reconstruct the amount of wealth tomorrow. And then given the optimal consumption, the policy function, I can calculate the optimal consumption tomorrow. That then can be put into the early equation that puts into correspondence the optimal consumption today and tomorrow. And from that, I can recover the optimal consumption today. And I'm particularly lucky if the marginal utility is analytically invertible. And then I know the optimal level of consumption today and an optimal level of savings today. I can put them together, and I have my MT point. What is this point? That's the amount of wealth which corresponds to this calculated optimal consumption. So, questions? Yes, very good.
Does the last step require another interpolation of consumption function over new?
The last one being number 5? Yes. No, because we started with a single number. We've calculated this number, and we add them together. And now to recover the full policy function, what is that, the policy function? It's going to be interpolated on some pairs of numbers. So for 1A, I've recovered this CT and this MT. For 1A, I recovered one pair of numbers. Now I go through many different A's, and I recover many different combinations of MT and CT, and then interpolate, and that's going to be my policy function in period T. Yeah. Yeah, very good. So we are still doing backwards induction, right? We started with capital T with your initial guess of the policy function. And so I already know the policy, or I've already approximated the policy in the next period when I'm doing this. So it's, these steps, they're embedded. This is going to be done many times for different A's. And this is going to be done many times in each iteration of the backwards induction. How does the early equation look then?
Yeah, so what you're ending up doing is that you're having
I think it's
motion for capital that is a differential equation. You're picking the rate of change, you're picking dots. So now you're working with the derivative of your value function, and you're evaluating that derivative of the value function becomes the derivative of the current consumption point.
And then, so if you have this analytical inverse, then you calculate it directly, it feels.
And then you're doing directly.
Yeah,
So
yeah.
a little bit an extension of your answer. In continuous time, you're not necessarily thinking about this as a backward recursion.
Oh, wait, was it a continuous time question or infinite horizon?
It wasn't.
Okay.
But you don't have to think about it as a backward recursion necessarily. And
Yeah.
it's useful to think about the continuous time version of that problem because it forces you into thinking about it in not a backward recursion.
That's a very good point. But it seems that everything is even easier.
It's easy.
It's easier, yeah.
But that's a general
Yeah,
point.
yeah.
Continuous time is not.
Yeah, okay. Okay, so another way to think about this is that given the early equation, we can think of this A that we use to kind of start this EGM step as a parameter. And so for every value of a parameter A, we get these two pairs of numbers, right, using these two equations. And so essentially, we're dealing here with a parameterized curve, which maps out the policy function as a parameter. I'm sorry, as a parameterized curve with a parameter which represents this A, this post-consumption value of wealth. Yeah.
If I had two things that I can invest in, A and B, then this becomes a two-dimensional.
This is part 4 of the talk. We'll get there. Hold your question. OK. Any questions to this? It's super easy. 11 lines in MATLAB. This is the replication or implementation of the full-blown consumption savings with stochastic returns, I think, over a life cycle, with some constants. And it flies. You can see, the running time is just, fractions of seconds, and I'm trying to make it really, really hard for EGM. And yet the errors that we get are much smaller. And so the errors are here measured by the residuals of the early equation calculated on a denser grid. And I mean, it's no surprise, right? We're using the early, in each point that we are producing, the early equation is satisfied exactly to machine precision. And therefore, it's impossible to beat in this problem. So a little bit more of the code. How do I do that? So remember, this is the solution with VFI. I mean, it's not too bad. And this runs much better on the newer Mac, actually. Before, I had more time to talk while it was working. But see, if we do EGM, this is it. And we get the same picture. And you know what? Each dot here represents a complete solution of the model. It's not iterating on time or anything. It's a complete solution. So it takes 0.003 of a second for a complete solution, as compared to 6 seconds for VFI. So, yeah. OK, any questions so far? I mean, it's a really, really, really nice trick. Of course, what's the limitation? The limitation is that we're solving consumption savings model, which is kind of simple, right? But the potential value is that we can do it many, many times. So you can think of a much more complicated model in which this consumption saving could be a small part of. All right, a few things to mention now about the credit constraints. So it turns out that if we have a monotone and concave utility function, then the end-of-period asset is a non-decreasing function of wealth. And you can show that as a pretty straightforward result. And what that implies is that we can now start being a little bit kind of specific about how we go through different values of A when we do the EGM step. And so, for example, if we start with A equals 0, okay, then the EGM will return a point that is defined by the interior solution at the point of wealth where it's optimal not to save anything. Okay, does it make sense? So if I run the EGM step with saving 0, I will recover the point of wealth where it's optimal to save 0. So where it's optimal to consume everything you have. And then due to this monotonicity, you will have that it will never be optimal to save anything to the left of that point of wealth. And that means that the consumption rule is just a 45-degree line, right? You will consume everything to the left of this point M super CC. So the solution looks like this, right? We first run the EGM step with A equals 0. And we will recover this point. This is wealth on the axis. We will recover this point. And then imagine that we're following some grid over A's, over savings. And we will recover that point, this point, this point. This is optimal consumption. This is wealth. When we connect those points, that's my optimal savings function. But what do I do here? Well, this is the region which is defined by the credit constraint. And due to this monotonicity result, I can just connect these two dots, right? Everything to the left of this first recovered point, it's optimal to consume everything you have. And this is super convenient. It doesn't work for every constraint like this. You have to rely on the theoretical properties of the problem. But in consumption savings, this is so cool, right? You run your EGM step to recover all of these points, and then you add one point in the origin. And if you're using linear interpolation, then you're done. Then your policy function is recovered. And it's also exactly, it's exact. It's analytical here, right? Because it's exactly 45-degree line. And another thing is that what I've already previewed is that this point is recovered exactly as well. This is the point where the credit constraint is not binding anymore. Or it's the point where you're breaking even. It becomes optimal to start deviating from the credit constraint to the right of this value of wealth. Does it make sense? And so this is that point which was impossible to recover with fixed grid. Because in the traditional methods, we put a grid on wealth. There's going to be some fixed points here. And for each of those fixed points, if we're really good and smart, we will recover the optimal consumption. But here, this corner will be cut off almost necessarily, because the location of this point is endogenous. And it will, in finite horizon problem, it will shift around too. And that turns out to be pretty important if you care about accuracy. Now, in the future, in the next step, we will need to recover the value function together with the policy function. And so it's worth saying that for all of the points of wealth to the left of this M sub CC, we know that the optimal thing to do is not to save anything, which kind of makes the policy function equal to the utility of consuming everything plus the continuation value of having no savings, right? It's the continuation value of zero wealth. Well, not necessarily zero wealth here if you have income, but it's a continuation value of zero savings. And this is a constant. So again, it appears that the value function has an analytical form in this credit constraint region, which is super handy. For the following reason. So what I'm trying to say is, right, to the left of this point, if I draw value functions, here the value function is just a shifted vertically utility. Why is it handy? Well, if you worked with fixed grids and if you've approximated a log function or utility function, the errors really accumulate where it becomes steep, especially close to zero. And here we're in the situation where you don't need to approximate to the left of that point. You have an analytical form of the value function close to zero. So that's another neat property of the approach. All right, any questions to EGM? How am I doing on time? It's terrible, I guess. No? Half an hour until the break. Okay. All right, so what happens in DCEGM? What I'm going to be talking is primarily from this paper, and this builds a lot on the Fellows paper in 2014. I already said everything here. Yeah, we made a solution method for empirical applications, as you will see. The idea in the preceding paper, in Julia Fellows' paper, is to identify the regions of the problem where the early equation is not sufficient for optimality, and then apply traditional solution methods in those regions. Okay, and this is similar to what we're doing without the taste shocks, and that's that nasty case. All right, so we will look at slightly different problem. We now want to introduce a discrete choice, okay? And what's the simplest way to introduce a discrete choice? I'm going to assume that there is a binary choice in each time period. And this binary choice is basically a choice between continuing to work or going into retirement. And this is represented by these two lines. If you're a worker and you, let me first say that if you decide to continue to work, then you have this Bellman equation, and there is a plus y over here in the intertemporal budget. So there's going to be wage. If you're retiring, there's no wage. You're just spending down the accumulated wealth. Now, I could just stop there and talk about the possibility of taking this binary choice in every period. And that would be totally fine, absolutely no problem. But I want to make an easier presentation. And therefore, and only for that reason, we will have retirement be an absorbing state. Okay? Because then, once you've taken the decision to retire, then the agent is back to the consumption savings model that we already looked at, and we don't have to worry about retirement. It's like we already have the solution. And therefore, I'm tracking the state of the person, and this is going to be an additional state variable. Okay? So if you're a worker, then you have a choice. If you're in a retiree already, then you're only solving the consumption savings problem, and you're staying a retiree. So we get a lot of questions whether this is important or not, and it is not important. We can allow discrete choices of any sort at any time period. No absorption is necessary for the method to work. In fact, this is what we're going to have in the application with Michael Key. OK, now assume that if I'm working, then I have this utility of work in the utility function, and everything else is pretty much the same. Believe it or not, but this problem also has an analytical solution, or semi-analytical, because I believe that these bars have to be solved numerically. Isn't it right, John? Oh, there's an analytical solution for those two. John had spent a couple of hours and solved it analytically on a piece of paper. The solution looks like this. And again, this is really, really handy because you can check your code against the analytical solution. The solution looks like this. We're looking at 3 exemplar or 4 exemplar optimal policy rules. They are, again, parameterized as number of time periods before the end, before the terminal period. And so if we look at one which is closest to the period, to the terminal period, this green one, it's, there is a credit constraint in this consumption problem. So you would expect to have a 45-degree section in the optimal consumption rule. And then, as you can see, it kind of starts behaving as it did before, and then discontinuously drops. And that has this, I believe these are linear segments which are defined, between the these are linear segments in wealth, which are defined in between the corresponding discontinuity points. And what is, we will get to the logic of why this happens, but this is what we should expect. This is the optimal way to consume in this problem. Interestingly, this property, which I want to highlight right away, is that as you move back from the terminal period, then you have more of these discontinuities. OK, so let's try to just run EGM in this setting. And that's how we started, essentially. We can think of how to do EGM step in this situation. Let's just do it. So the goal for this generalization is to still avoid root-finding operations, which that seems to be the kind of the main selling point of the whole method. And we want to try to keep efficient treatment of the credit constraint. So the idea is to run EGM for each discrete choice at every state. OK? We can do that. Given the discrete choice, given the value of d, we can do the EGM step as before. Now, after that is done, we can compute the value function corresponding to that discrete choice d. And once we have computed the value functions, then we can actually decide by comparing these value functions what is the optimal discrete choice, right? So this calls for the calculation of the upper envelope of a set of value functions recovered by the EGM method. And that allows us to reconstruct also the overall consumption rule by kind of stitching together the corresponding consumption rules for each of the value functions. Right, so no root finding, probably efficient treatment of credit constraint, no need to compute, need to compute the value function and need to calculate the upper envelope. So there is more work to do. And to kind of previewing the result, this is going to be 100 times faster than VFI, not 1,000 times faster. One important theoretical foundation is the answer to the question, is Euler equation still characterizing the optimal choices? And the answer is provided by this paper by Clausen and Straub. Yeah, the title is updated, I think. They basically say that in the problems of this class, the optimal continuous choice never falls to the kink, even though there are kinks in value functions. And that means that the first order conditions still apply. All right, so let's proceed. Terminal period. The blue line is retirement value. The green line is the work value. What do we do in the terminal period? With our timing assumption, which is specified here, the timing assumption calls for the wage for the work decision to be received in the beginning of the next period. Okay? And that kind of makes working completely useless in the terminal period. And therefore, it's clear that for every value of wealth, it is optimal to retire. Can you see that? So we are just comparing the value functions here. Now, as we go to capital T minus 1, this green line is still the value function of working. And you can see that I kind of stopped it here because the graph did not continue with this analytical continuation. But there's going to be the intersection point, something like this. And if we calculate the upper envelope, then we have the true value function, the one that corresponds to the Bellman equation. And what happens here, the blue line is the value of retirement, and the green line is the value of work. This is that analytical continuation. And here's the point of wealth, which decides whether you're retiring or you're staying at work. So essentially, if you're wealthy enough, then you take retirement. If you're to the left of this intersection point, it's better to remain working. Does it make sense? Okay, and immediately we see, that this discreteness in the problem brings about this kink in the value function. Okay, and so the kink in the value function is there because we have discreteness in the problem, because we have these choices to kind of switch between. And moreover, this kink, because of the shape of the value function, creates this non-convex region in the value. We will see that more in detail in a little bit. But remember, this is a dynamic problem. This value will feed into my optimization problem on the previous time period. And now that implies that my previous time period optimization problem is not convex anymore. Okay, and that's going to bring that's going to cause a lot of trouble. Now, if I look at the optimal consumption from this combination of values, there is an optimal way to consume if you're a retiree, and there's an optimal way to consume if you're a worker. And if you put them together, then you get this discontinuity in the optimal consumption rule. So how do you, this vertical line on this graph is not there. It's not connected, right? It goes 45-degree line, then deviates from the credit constraint, and then just discontinuously jumps here. And this is the optimal consumption corresponding to retirement. And essentially what happens here is that because if you're retired, you don't get that disutility of work, and it becomes optimal to consume a little bit less. That's one way to think about that. If you compare kind of around this discontinuity point. Another way to think about this is to say that, in the end of the day, you're equalizing the marginal value of wealth to your marginal value of consumption. And in this point, the marginal value of wealth, the derivative of the value function, changes discontinuously. And that corresponds to this discontinuous change in the optimal consumption that follows from the marginal value of consumption. I'm sorry, say it again? Between here? Oh, before here. Oh, this one. Okay, that was there before. That was this one. So the retirement problem still has the credit constraint, and therefore we expect the optimal consumption rule to follow the 45-degree line until some value. Remember, you're working here, and because you're working, you will get wage tomorrow, and that implies that there is a certain level of wealth up to which you want to consume everything to be on the optimal path. Okay, so this is what happens. These specific value functions intersect due to the trade-off between income and this utility of work. The upper envelope of the value functions has a kink. That's the natural, that's fundamentally what happens here. The combined consumption functions have a discontinuity. Now, this kink is something fundamental to the problem, and it's due to the fact that we have discreteness. Like, how would we change the problem to get rid of this kink? That's a question to ask yourself. Right, now, okay, let's just continue. Okay, we have a kink, whatever. Let's just continue and do the previous period calculation. And this is what we did with Bertels some years ago now. And we are running EGM. We are recovering those pairs of points. And it turned out afterwards that we were also sorting them somewhere in the algorithm. The points on wealth, right? This is still wealth. And I'm plotting value functions. And this is the value function of a worker, the green one. And we're just doing the EGM step like we decided to do, specific to each discrete choice. And suddenly this stuff appears, right? And if you zoom in, you see that the value function is just crazy for some reason. It just goes up and down in this particular region of wealth. And it was very mysterious until we realized that if you also look at the early equation that produces these points, this is the residual of the early equation. And again, the vertical lines shouldn't be here. It just turns out that for the same range of wealth, the early equation has two solutions. Okay? It has two solutions because it's tracing out two local optima in this non-convex optimization problem. And so essentially what was happening is that we were running EGM. We were calling EGM step for different levels of wealth. And we got in return a combination of consumption, well, it's not plotted, and wealth, and recovered the value for that consumption choice. At some point, the endogenous points of wealth were kind of repeating themselves. And once we sorted them, then it started jiggling like this. So essentially what's going on? You're solving first-order conditions. You get 2 points, which are stationary, but only one is an optimum. How do you find the optimum? And we're solving the value equation as before, right? No, I'm not going to skip to that. We are trying to solve, we're trying to find the maximum of the Bellman maximant. Well, the answer is the same. We can just look at the upper envelope. And that's kind of the key approach here. Okay, so what happens here?
This was two solutions to the first order condition. Was the other one a minimum?
These are two stationary points. They're two local maxima. No, does it make sense? Yes, it does, because there's a discontinuity.
They have the same value attached to them.
For some values of wealth, let me point to this graph. For some value of wealth, the early equation has two solutions. The reason there are two solutions is because the early equation itself in this formulation is discontinuous. right? So this is cash in hand. This is my wealth. And this is, this should be savings, I suppose. No, this is cash. That's right. So we're solving an early equation, but implicitly in the EGM step. And so the early equation, because of the kink in the value function in the next time period, it has a discontinuity. So look at the blue line. This vertical doesn't exist. The blue line goes like this. And my method traces out the 0 of the early equation. But as you change the consumption level, then this is the residual of the early. The early equation shifts down, and for some values, it has 2 solutions. And we're tracing out both of them.
Is this the solution where I have retired and where I have not retired?
You're still a worker, but this is a very good question. So why do we have these 2 solutions? Well, this is a deterministic problem, right? And I'm still a worker. I'm only looking at the worker, as I've explained. I'm about to get too close to that kink point tomorrow, where I may be on one side or the other side of the kink. And so this is kind of an echo. It's a reflection of the kink point in the period t+1 that shows up in the early equation when we're solving for the optimal consumption in period t. So in practice, this is how it happens. Imagine that I'm going through a grid of savings of A's, and I'm recovering this point. I'm plotting, this is wealth, and this is value. This is value function as far as yes, this is value function. And so I'm going through different possible levels of savings, and I'm recovering this point. Okay? And then at some, I take another, I save a little bit more. I save a little bit more after this point, but I get out this point here from my EGM step. And so it kind of bends back. I get a lower value of endogenous wealth that is optimal for a little bit higher savings compared to this point. Okay? Why is that? Well, because that a little bit more savings actually puts you on the other side of the kink tomorrow. And now it's optimal for you to retire tomorrow, and you're consuming according to a different segment of the optimal consumption function tomorrow, and the marginal utility of that consumption has changed and fed back into the lower value of wealth today. And then you continue further, and you have this, this value now becomes a correspondence. So we are following all of the points that correspond to the solutions of the early equation, even though some of them are suboptimal. So we're following all of the points that solve the first order condition. And now we have to basically filter out those which are suboptimal. How do we do that? As I've already said, this is the value. And we are maximizing the value in Bellman equation. So actually, the solution is just the upper envelope of this correspondence. Okay? Now, this red line now corresponds, shows the optimal value, which is not subject to the suboptimal points, which is not taken into account the suboptimal, does not include the suboptimal points recovered by the EGM step. And the EGM step recovers those suboptimal points because it's only the first order condition. And, well, the conclusion here is that suddenly we have this another kink. Now, the value function, which is the red one, will have this additional kink, which does not correspond to a change in the discrete choice between, this wealth on the left and this wealth to the right. This kink is just, like an echo of the kink tomorrow that corresponds to changing your discrete choice tomorrow. Does it make sense? So this is the exact value of wealth here, which puts you on the kink tomorrow, which is substantial. Yeah.
But if that function were sufficiently different, shouldn't you have an echo of the kink the period before as well? So you basically, the kink at t+1 gives you a kink at t, and then this kink at t that we derive from
Yes, perfect intuition. So what ends up happening is this, okay? So kinks accumulate because it all starts with a kink which corresponds to the actual, economic change, but then in the deterministic setup, they all replicate back in the backwards induction. Yeah, and let me show. So this is kind of the main picture. The kink in the value function, which corresponds to the switch between being retired or work, then kind of, this is a picture that shows everything in one. In T+1 will create this kink in T just because of the non-convexity. And then this one will create another kink on the previous iteration. And you go from 2 discontinuities in the consumption function to many discontinuities in the consumption function as you go back through time. And this is actually exactly what we saw in what was the analytical solution, right? That explains why there are so many discontinuities as you go back from the terminal period. That's exactly what happens. Okay. Now, how do we deal with that? Well, we can do the upper envelope, right? That's not that hard. The hard part is how do you detect that you have to do the upper envelope? And so one approach is actually relies on this monotonicity, again, on the monotonicity of the savings function as a function of wealth. And essentially, let me not go through the steps. Essentially, what happens is that if you call EGM step for a monotonically increasing grid of savings, then you can actually detect the fact that the recovered endogenous wealth went back. Okay, and if you detect that kind of back bending, then you know that there will be a secondary kink in this interval between this point and this point, and then you can invoke the upper envelope procedure for that particular interval. That's the idea. So it's essentially shows it here, right? So this is the order in which we recovered the points as on the monotonically increasing grid of wealth, of savings. And then after point 11, you went down to point 12, and then you continued. And because there was this shift down, you know that you need to calculate the upper envelope. And once this intersection point is located, then you can actually also remove the points which are suboptimal from the corresponding optimal consumption function, because the optimal consumption function, or this is a correspondence again, it looks like this, coming out kind of raw from the EGM step. And that's because these points over here and these points over here are suboptimal according to this calculation, and we can delete them as well and install the discontinuity, in between here. And yeah, you can add some points to make it really vertical if you want to preserve accuracy. Okay, any questions to that? So just let's go through it once again. The D-specific value functions intersect. That creates due to the trade-offs, the upper envelope has the kink in the T+1, and the derivative of the value function has a discontinuity, that kink, and that discontinuity in the derivative translates to the early equation, which now has 2 solutions, and you get this, what we call a secondary kink in the value function. There is an alternative way to detect kinks, which does not rely on the monotonicity of the savings functions, which could be useful in other applications, in some other settings rather than the consumption savings. It has to do with kind of looking, sorry if you read the slide, kind of looking at this picture here. And if your next point on the sorted grid makes your value function kind of turn left or right, if you go like this, and in the same time the underlying consumption makes a jump, that detects that this is a suboptimal point here. And that can actually be done for every combination of these points. So this is the paper which I reference, and it's called, it talks about this fast upper envelope scan. It also applies in multiple dimensions, so it's useful. Okay. So this is essentially the fact of life, okay? The solution to this problem looks like that. And the sad truth is that whatever method you use to solve a problem with continuous and discrete choices without any, in the deterministic form like this, you will have to deal with that. And your method will have to deal with that. And there's no way around it, right? This is just follows from formulas. What happened to our full DCEGM algorithm? Well, now we have this additional step which computes the secondary upper envelope to get rid of the secondary of the zigzag, to get rid of the suboptimal points on the value function. And the algorithm kind of becomes longer, right? So we start from the terminal period. We do the EGM step for each discrete choice. We compute the d-specific value function and consumption rule. Then we get rid of the secondary kinks. And then we compare the value functions to find optimal switching points, to find the primary kinks. And that reconstructs the solution. Yeah. Should I? Let me do a couple of examples here. When is the time to take a break? It could be now. Okay, let me do a couple of examples and then we take a break. So I want to show this setting first, which I forgot to show for the EGM. So look over here. Does it show over there? So I'm gonna take a model, and I'm going to adjust its parameters such that the discount factor equals exactly 1 over 1 plus r. Okay? And this is a deterministic model. We expect completely flat consumption paths if we simulate from this model, right? Do we agree on that? And I'm going to solve this model with VFI. This is the sort of test which is a very good idea to run. And we labeled it Make It Flat because we had a lot of conversations with Mike Keane on this, and you may hear from him. Well, anyway, this is the Make It Flat test with VFI solution. What happens? I'm starting a couple of simulations. This is wealth now, and this is age. We have a 25. Oh, this is very small numbers, but this is 25 here. Can you see those lines? We start two consumption paths at two different levels of wealth. And I want to look at two because, MATLAB zooms in so hard that you will never get anything flat. Consumption is simulated in the usual way, as you would imagine. It basically takes the optimal consumption choice, calculates the next wealth, and so forth. And then you can see it starts off kind of flat because there's not much error yet, right? But then as we go forward, the error accumulates. And so it seems to me that the numerical error over here starts to affect the solution, and then it kind of overcompensates towards the end of life. But now if I switch to EGM solver over here, the effect is that first it's very fast, and second it's very flat. Right? We get a really, really nice continuous functions. Now, what's even more surprising is that I can do the same thing with the retirement model. Okay? We've talked about the retirement model with deterministic choice between retirement and savings. This is the same condition here. And what's your prediction? It takes a little bit longer, and it makes more graphs here. But this is kind of fascinating. So in this plot, we're again simulating two people, starting off with different levels of wealth. And they're going through life, performing optimal consumption decisions until they reach a point where they decide to optimally retire in their life. And they retire and then continue taking the consumption decisions until they die at 25. And you can see these two people retire at different times, at different periods. And they are completely flat. They are smoothing out their consumption perfectly, at least to the numerical precision here. This is time, and this is consumption.
Right, but are they starting out with different wealth, or are they starting out with different
they are starting out with different wealth. And they are getting the same income. They also consume more. Yeah, let's, well, I think it's the same. Well, let me check in the code. But the point I want to make here now is that, you know how the optimal consumption rules look? It's over there. This is the worker and the retiree. This picture is familiar. This by now is also familiar. It's full of discontinuities, this optimal consumption rules. And yet, you shouldn't think of this as implying that the simulated consumption path is not flat. This is an example of our rational assumptions on these decision makers playing out perfectly, in the sense that even though the optimal decision rule is crazy and discontinuous and consists of this many different parts, the decision maker somehow is able to compute this completely flat consumption profile through these decision rules, right? And optimally jump between different segments of the decision rule such that the simulated consumption profile is completely flat. Let me check how I initialize this too. Okay, let's take a 10 minutes break or.